Section 1 of Chapter 9, Radicals and Rational Exponents. We will also discuss radical functions. Here we will determine the nth roots of numbers and evaluate radical expressions. Use the rules of exponents. Think back to Chapter 5, Section 1. Use the rules of exponents to evaluate or simplify expressions with rational exponents. So Section 1, we dealt with exponents that were either positive integers, negative integers, or zero. These are just counting numbers and their opposites. Here we will discuss exponents such as 3/4, 1/2, 1/3, etc. What does the numerator of the rational exponent mean for us? What does the denominator of the rational exponent mean for us? Use a calculator as well as our brains to evaluate radical expressions and evaluate radical functions and find the domains of radical functions. Recall that the domain of a function is the set of input values such that you will get an output value from that function. In other words, if you plug in a number for x, there corresponds a value of y. And that is a real number for y and a real number for x. So all of the usable values that you can plug into a function defines the domain of a function. As we look at the definition for the nth root of a number, we see some examples listed to the left. For example, the number 9 can be expressed as 3 squared. Recall that 3 squared represents 2 factors of 3. Thus, 3 multiply 3 will give us 9. Rewriting 9 as 3 squared, we refer to the value of 3 as the base or the root, and we refer to 2 as the exponent. Now, because we can write 9 as 3 squared, this means that the square root of 9 is equal to 3. If you can rewrite a number as some integer squared, then the square root of the original number here, the square root of 9, is equal to 3 because we can rewrite 9 as 3 squared. Likewise, what about the number 25? Note here that we can express 25 as the square of -5. In other words, squaring -5 multiply -5. We have 2 factors of -5. If we multiply -5 to -5, the negatives cancel, and thus 5 times 5 is 25. Again, as we see here, the base or the root of our number, -5, with exponent 2 results in 25. Thus, the square root of 25 is equal to -5. We're going to see that relationship between squares and square roots, cubes and cube roots, thus powers of n, a power of 2 or a power of 3, corresponds to a square root, a cubic root, in general, an nth root. So the nth root of a number is the result of raising a number to the power of n. Notice here the definition for the nth root of a number says, let a and b be any real numbers, and let n be an integer such that it's at least 2 or more. If a is equal to b to the n power, in other words, is it b squared, is it b cubed, is it b to the 4th, b to the 5th power? What is the power of our root b? If a can be rewritten as b to the n power, then we can say that b is an nth root of a. In other words, we make numbers powers of numbers to get other numbers. If our exponent n is 2, then we say that our root is a square root. If n is equal to 3, we say that our root is a cubic root. Anything larger than that, for example, if n is equal to 4, for our power of 4, our radical in this case here would be the 4th root. For n equal to 5, the 5th root, 6th root, etc. But for n equal to 2, we can refer to it as the 2nd root, but it's typically referred to as the square root. We could refer to it as the 3rd root, but typically we have a common expression, and that is the cubic root or the cube root. An interesting one here would be the value of 64. Notice here that number 64 can be rewritten as the expression of 4 cubed, where 4 is our root and our exponent is 3. In other words, 4 times 4 times 4 gives us 64. So we see here that the cubic root of 64 or the cube root of 64 is equal to 4. 64 is also interesting because what about the square root of 64? In other words, what is the number that you square that results in 64? Well, remember that for square values, notice that for 25, if you square -5, it gives you 25. But also, if you square +5, it gives you 25. So for square values, we can square a negative value or the positive value of that number, -5 or +5, when squared gives us positive 25. Note here, when we cube a -3, it results in a -27. However, when we cube A positive 4, it results in a positive 64. There will be a relationship between our exponents, whether they are odd or even, and how they give us a resulting value. If we square a negative, it always results in a positive, because multiplying two negative numbers, -5 multiplied -5, will always cancel the negatives, resulting in a positive 25. However, cubing a -3 means we have three factors of -3. Multiplying by three negative values, the first two negative factors cancel. However, the positive 9 multiplied -3 now gives us the -27. Thus, the cubic root of -27 is -3. If we cube a negative, if we raise a negative number to an odd power, the third power, the fifth power, seventh, ninth, etc., if the exponent is an odd number, then raising a negative value to the power of an odd number will always result in a negative. However, raising a negative number to an even power, 2, 4, 6, 8, etc., that will always result in a positive. But note for a number like 64, we say that the cube root of 64 is 4, because 4 cubed is 64. Notice also that the square root of 64 is equal to 8, because 8 squared is 64. Also, the square root of 64 is -8, because if we square -8, -8 multiplied -8 is 64. Now, in this text here, we will state when we want to work with the positive roots and the negative roots. Typically, when we deal with numbers such as 64, the square root of 64, yes, is positive or -8, but we will specify when we want to work with the negative root. So normally, more often than not, when we look at the square root of positive values, we will express only the positive root. But keep in mind that the negative and positive root are possible values. -8, +8, when squared, give you 64. But for moving forward, if it's not expressed, we will just use the positive root value. 16. 4 factors of 2, in other words, 2 to the 4th power, results in a 16. Thus, the fourth root of 16 is equal to 2. What else about 16? The square root of 16 is 4 and -4. Thus, we will say the square root of 16 is 4, because 4 squared is 16. Some numbers have more than one nth root. As we said, for example, both 5 and -5 are square roots of 25. To avoid ambiguity here about which root you are referring to, the principal nth root, or the positive root, of a number is defined in terms of a radical symbol. Here, our radical symbol here, whether it's the square root, cube root, fourth root, etc., has our radical notation here, where we have our radical sign, and the value of n is expressed as the root or the index. So the principal square root of 25, which is written as the square root of 25, is the positive root 5. If we refer to the negative square root of 25, it will be expressed with a negative sign out in front of our radical symbol. Note also here, for the square root symbol, our index of 2 is not expressed. If you have a radical sign with no given index, here there is not a value for n within our radical symbol. Therefore, to the reader, it is understood that this radical sign is for n equal to 2. This is the square root of 25, which is 5. Numbers such as 1, 4, 9, 16, 25, 36, 49, 64, 81, and you can list this forever. There are an infinite number of perfect squares, but these are perfect squares because they have rational square roots. In other words, the square root of 1 is 1. 1 is a rational number because it's a whole number. Remember, any whole number can be written over 1, thus making it a rational number. The square root of 4 is 2. 2 is a whole number. It's an integer. It's a real number. It's positive. But the square root of 4 equal to 2, 2 is a rational number because it's understood as a fraction 2 over 1. Remember, we can always write a whole number over 1. Square root of 9 is 3. Square root of 16 is 4. Let's keep going with it. The square root of 25 is 5. Square root of 36 is 6. And again, why are these the numbers? Why are these the perfect squares? It's because 1, 4, 9, 16, 25, etc. These are the results of squaring some integer number here, or some fractional number. We square 1 to get 1. We square 2 to get 4. We square 3 to get 9. We square 4 to get 16, etc. Numbers such as 1, 8, 27, 64, and 125 are called perfect cubes because they have rational cube roots. In other words, the cubic root of 1 is 1. The cube root of 8 is 2. The cube root of 27 is 3. Why? It's because 1 to the power of 3 is 1. 2 to the power of 3 is 8. 3 to the power of 3 is 27. Let's also bear in mind here that for perfect cubes, negative numbers can also be perfect cubes. Let's consider the numbers -1, -8, -27, -64, and -125. If you cube a -1, this is -1 multiply -1 multiply -1. Well, that's -1. Cubing a -2, having three factors of -2, is -8. As we see above, if we have three factors of -3, -3 to the power of 3 is -27. Thus, for each of these numbers, as we begin to learn these numbers and learn the techniques for the memorization here, for perfect squares are only positive numbers. Keep that in mind. Perfect squares are only positive numbers. However, perfect cubes can be positives, such as the examples listed here, 1, 8, 27, 64, 125. You keep listing. 125 is 5 cubed, so what is 6 cubed? It's 216. 7 cubed, I believe, is 343. 8 cubed is, I'm not sure, it's somewhere maybe in the 500s, 524, 514. I'm not really sure, but the point is, you just keep listing out those numbers, and if you throw a negative sign out in front of the perfect cubes, those negative values are also perfect cubes. Because you can take the cubic root of a negative number. Why? It's because when you raise a negative number to an odd power, such as 3, that results in a negative number. Thus, for -27, the cube root of -27 is in fact -3. The cube root of -64 is in fact -4. The cube root of -125 is -5. So if taking the cubic root of a negative gives you a negative. Taking the square root of a negative, well, what about that? Can you take the square root of a negative? Well, no, right? Because all of these square values result in a positive. So we can only take the square root of a positive number because squaring numbers only results in a positive. For real numbers, that is. When you take a real number 3 and you square it, you get +9. When you take a real number and square it, such as -5, when you square -5, you get +25. Our outcomes of squaring values are always positive. Thus, when we take square roots, they can only be of positive numbers, such as 9, 25, the fraction 4/9, the fraction 81/4. All of these rational numbers that happen to be perfect squares, when you take the square root of a positive rational number that's a perfect square, you're going to get out a rational number that may be positive or negative. But here, for the ambiguity, we're going to keep only the positive root here in consideration for the positive square root values or the positive nth root values. Now, again, you can take the cubic root of a negative number, but you can only take the square root of a positive number in order to get out a positive value. In section 6, we will discuss taking the square root of a negative number. As we say here, the square root of a negative number is undefined, and as you will see in your calculator, the square root of a negative number is undefined. But in section 6, we will define imaginary numbers, and imaginary numbers are defined to be the square root of a negative number. This application is very important as we talk about circuits and electricity, as electricity, when it moves in the opposite direction, it will be expressed with a negative value. Thus, the square root of a negative number for electricity moving in the opposite direction must also be computed. Thus, we have the imaginary number line that is defined to be the square root of negative values. We will use the definition of the nth root of a number as we discuss the principal nth root of a number, using our radical symbol notation to further evaluate and simplify our radical expressions. Let a be some real number, so a is representing some real number or variable expression that has at least one nth root. The principal nth root of a is the nth root that has the same sign as a. In other words, if we are taking the nth root of some positive number, the principal nth root is going to be a positive value. If we are taking the nth root of a negative number, our principal nth root is going to be a negative output, some negative value. So here it says that if it has the same sign as a, it is denoted by the radical symbol notation, the nth root of a. We can refer to this as the principal nth root or the positive nth root. The positive integer n is the index of the radical. And again, if n is equal to 2, we omit the index and just write the radical notation square root of a rather than having the second root with our 2 noted. If it's not in there, it is understood to be the square root. If a number is expressed, that is letting us know how many factors or what our exponent is that we wish, that we desire. So again, here the nth root of a, the number a is referred to as the radicand. So whatever number or expression is underneath our radical sign, our radical symbol, the number or expression under the sign is referred to as the radicand. We will look at evaluating a few of our expressions here. For part A, it says the square root of 36. the square root of 36, so it's indicating that our root here, or our index, is 2. We have an index equal to 2. So what number corresponds to 36 such that when you square this number, it gives you 36? The square root of 36 is equal to 6. And again, we are using the principal root because 36 is a positive number. Thus, because we have a positive number here, we're going to get a positive output. The square root of 36 is 6. Our principal nth root, the principal square root of 36 is 6. Why? It's because we can express 36 as 6 squared. Because we can write 36 as 6 squared, which is 6 times 6, this tells us that the square root of 36 is 6. Why is it? Again, it's the square root because when you square the root of 6, 6 squared is 36, thus its square root is 6. Makes sense? What about for part B? Part B has the negative square root of 36. So part B and part A are very similar to one another, right? Because what this says here, whatever the square root of 36 is, place a negative out front. In other words, this is the positive square root of 36, which what is the positive square root of 36? It's 6. What is the negative square root of 36? Well, we also know that when we square negative 6, it will give us 36. Thus, for part B, this indicates the negative square root. In other words, if you just isolate this expression here, consider the negative a factor where the negative 1 out front is multiplying the square root of 36. Well, we just said this expression here is 6. Thus, for part B, what we have here is the negative of means multiply the negative of the square root of 36. Negative 1 multiply the square root of 36, where we have 6. Negative 1 multiplied 6 is negative 6. Just in other words there for part B, what is the negative root that we get when we take the square root of 36? Keep in mind that's also negative 6. Why? Because when you square the negative 6, negative 6 multiplied negative 6 is positive 36. And just giving our reason there, reasoning for why we have that square root value. For parts C, D, and E, for part C, we were looking at the square root of negative 4. In other words, what is the root that you square to get negative 4? What number do you square to get negative 4? Remember, when you square any number, it's always positive. Squaring any number results in a positive value. Squaring a positive 5 is 25. Squaring a negative 5 is positive 25. So squaring a negative is positive. Squaring a positive is positive. And of course, squaring 0 squared is 0 times 0, which is just 0. So there is no number such that when you square some number A, it's going to give you B. Or that vice versa. There is no number A such that when you square B, you get A, which is negative. Therefore, for part C, the square root of negative 4 is a non-real number. Try putting that into your calculator. It will tell you either undefined or non-real. Most likely non-real because that's what it is. In section 6, we will define imaginary numbers. Again, we work with real numbers, right? That's what the book's telling us. Notice there in the definition, let A be a real number. Here, negative 4 is not a real, or excuse me, negative 4 is a real number, but when we take the square root of a negative, it does not give us a real number, it gives us an imaginary number, according to section 6. Here we work with real values. We plug in, we take the square root of some real number, it should give us back a real number. Turns out that when you take the square root of a negative number, it's going to give us an imaginary number back. So here for part C, square root of negative 4 is non-real. But what about for part D, the cubic root of 8? What is the cube root of 8? In other words, what is a root or number such that when you cube it, raise it to the power of 3, it'll give you the value of 8? A number times a number times a number. That's 2, right? 2 times 2 times 2 will give us 8. Thus, the cubic root of 8 is 2. And why is that the case? The cube root of 8, in other words, what number or root do you cube? If you cube a 2, 2 times 2 times 2, 2 times 2 is 4, times 2 is 8. So that's why we see the cubic root of 8 is in fact 2. And for part E, what happens here? Uh-oh, we have a negative under the radical. So as we saw in part C, the square root of a negative is non-real. So we would think that for part E, right? That isn't the case. We said that according to section 6, but we'll see later on, the square root of a negative is defined to be an imaginary. But what about the cubic root of a negative? If our index here, which is 3, if our index is an odd number, such as 3, 5, 7, 9, etc., then we know that the number underneath can be negative. And according to the principal nth root, because this value is negative, the cube root is going to be negative. What is that negative number with an index of 3? What is this number such that when you cube this number or raise it to the power of 3, it will give you negative 8? Well, if we cube 2 to get 8, then surely we will cube negative 2 to get negative 8. Negative 2 multiply negative 2 is positive 4. Multiply that third factor of negative 2 is negative 8. Thus, for E, the cube root of negative 8 is negative 2. The properties to keep in mind for nth roots. Property 1 here says that if A, the radicand, is a positive real number and n is even, then A has exactly 2 real nth roots. One is positive and one is negative, as we saw there. For example, 81 has a positive square root and a negative square root. Because as we see here, squaring a positive 9 results in an 81. 9 times 9 is 81. Also, squaring a negative 9. Two factors of negative 9. Negative 9 multiply negative 9 is positive 81. Thus, to express each of these roots, one positive called the principal root, one negative called the negative root, the principal root, square root of 81, the negative root, negative square root of 81. Thus, 81 has 2 roots, one positive and one negative. However, property 2, if A is any real number, so if our radicand A is a real number and n is odd, so if we have an odd numbered index, then we're working with an odd number of factors, then A has only one real nth root, which is denoted by the nth root of A. In other words, the cubic root of 27 is not plus or minus 3. The cubic root of 27 is 3. The cubic root of negative 27 is negative 3. However, the square root of 25 is positive 5 or negative 5. The square root of a perfect square is going to result in 2 real roots, according to property 1. However, for property 2, if n is odd, such as the cubic root or the fifth root, the cubic root of a perfect cube, the fifth root of a perfect fifth power, these are going to result in one and only one value. Property 3 says if our radicand is negative, if a is a negative number, and n is even, then A has no real root. As we saw there for part C, the square root of negative 4 is non-real. There is no number such that when you square a number, it's going to result in a positive. Squaring a number will always result in a positive or 0. It will never result in a negative. Excuse me. Part C, no number will ever square to give you negative 4. So number 3 there, property 3 says, if A is negative and our index is even, so square root, fourth root, sixth root, etc., then our radicand cannot be negative. It can only be positive or 0. However, if our index is odd, 3, 5, 7, 9, etc., if our index is odd, then A can be any number it wants. If A is negative and our index is odd, then our outcome is negative. If A is positive and our index is odd, our outcome is positive. If A is positive and our index is even, then we will get a positive and negative outcome. If A is negative and our index is even, then our outcome is not a real number. As we have worked with arithmetic, we have seen that the operations of addition and subtraction are known as inverse properties, because we know that when you add a number A and then subtract that number A, those operations cancel out. Thus, the additive inverse is subtraction, and the subtraction inverse is addition. Likewise, multiplication and division are known as inverses. Well, again, think about that. If addition and subtraction are inverses, multiplication, which is a repeated addition, division, which is repeated subtraction. So to multiply by 4 and then to divide by 4 is to cancel out. Thus, multiplication and division are known as inverse properties. What we're going to see here is that raising any base to the power of n and then taking the nth root of that value is going to cancel the exponent, leaving you with your base. In other words, here, powers of n and nth roots are going to cancel with one another. Thus, the exponents and the radicals are going to be viewed as inverse properties. The inverse properties of nth powers and nth roots. Our inverse properties, as we see to the right, we have some examples listed. The square root of 4 squared is equal to 4 because the square root of 4 is 2, and thus 2 squared is 4. Notice there that essentially what we did there is we canceled the exponent of 2 and the radical notation there, the square root, because the base or the index of our radical was 2 and our exponent is 2, they cancel, leaving us with our radicand of 4. Likewise, the cubic root of 27 raised to the power of 3, the cubic root of 27 is 3, and 3 to the power of 3 is 27. Thus, the exponent of 3 and the radical symbol, cubic root, cancel, leaving us the radicand of 27. The inverse properties of nth powers and nth roots in general state that let a be any real number, as we see over there, 4, 27, 16, negative 243, these are all real numbers. Let n be an integer such that n is greater than or equal to 2. So it must also be integer, so not working with any fractional values just yet. We'll see that later on in the video. These are integer values such as 2, 3, 4, 5, etc. Just add 1 to the exponent, and those will be our integer values that we're discussing here for n. Property 1 states that if a has a principal nth root, then the nth root of a to the nth power is equal to a. In other words, there our exponent is n, our nth root radical cancel, leaving us the radicand of a. But it also shows here that if we have the exponent on the inside, there's something to be considered. If our exponent is on the inside of our radical sign, then property 2 says if our exponent and thus our index is odd, then the nth root of a to the n power, again, notice the exponent, notice the difference between 1 and 2. Here, the exponent is underneath the radical sign. It's a part of the radicand. Our radicand is no longer a. Our radicand is now a to the nth power. So property 2 says if n is odd, then the nth root of a to the n is equal to a. In other words, you can cancel the exponent and the radical sign, leaving you with the output of a. However, if n is even, we need to consider our absolute value notation. It says here that if n is even, then the nth root of a raised to the n power is equal to the absolute value of a. In other words, here, if we have the square root of negative 5 squared, then we get here the absolute value of negative 5, which is 5. And the reason why this is the case here, what we can just consider doing for this is what happens underneath the radical sign. If you square negative 5, remember that if you square a negative number, it always results in a positive. So under that radical sign is 25. And the square root of 25 is equal to 5. So that's why we consider the absolute value for when n is even. If a is a negative number, our cancellation would leave our output with a negative value, but it must be positive because we can't have a negative value under the radical sign. Squaring that negative value, squaring the negative 5 results in a positive 25, and the square root of positive 25 is positive 5. But if we don't simplify the square of negative 5, if we just try to cancel the exponent 2 with the radical sign, then we're left with negative 5. But remember, as we just said, the square of negative 5 is positive 25. So as we have negative 5 under the radical, we place the absolute value signs around it because the absolute value of negative 5, in other words, the distance between 0 and negative 5, that's what absolute value is. In other words, whatever number is in the absolute value bar is just dropped to negative, indicating a positive 5. Why is it positive 5? The square of negative 5 is positive 25, and the square root of positive 25 is positive 5. So our inverse properties indicate to cancel the exponent with the radical. As long as the exponent and index are exactly the same value, you can have that cancellation. But if we have an even exponent and thus an even index with a negative value of a, such as negative 5, then we must consider the absolute value by changing that negative 5 to a positive 5, as our inverse property cancels our nth power and nth root, giving the absolute value indicating a positive outcome. For part A, B, C, D, and E, evaluate each radical expression. For part A, we have 4 cubed underneath our radical sign. Therefore, our radicand is 4 to the third power, which we can evaluate 4 to the third power is 64. Thus, what is the cubic root of 64? The cubic root of 64 is 4. Now, using our inverse property, because n is odd, what can we do here? We can cancel the exponent of 3 with our radical notation, cubic root, leaving us for part A a value of 4. The cubic root of 4 cubed is 4, because the cubic root of 64 is in fact 4. Mathematically, using the inverse property, canceling out the exponent of 3 in the radical notation, we get 4. What about for part B here? Noting again that our exponent in index 3 is an odd number. Remember, what are those odd numbers? 1, 3, 5, 7, 9, 11, etc. So those numbers that when you divide by 2, you don't get a whole output. Even numbers such as 2, 4, 6, 8, 10, etc. all contain factors of 2. They all can be divided by 2 wholly. So here for part B, the cubic root of negative 2 raised to the third power. So our exponent is underneath the radical sign. Our exponent is odd. Canceling the exponent with the radical sign, part B, we're left with negative 2. We can also see this because under the radical, if you cube negative 2 multiply negative 2 multiply negative 2, this results in negative 8. And as we've seen in the video, the cube root of negative 8, what number do you have to cube to get negative 8? Well, as we see, it's negative 2. Thus, for part B, the cubic root of negative 8 equals negative 2. Using the inverse property, canceling the exponent with the radical, for part B, we get negative 2. However, for part C, you notice there it fits property 1. Property 1 states that if we have the square root of some number, as we do the square root of 7, notice here that the exponent is not under the radical sign. It's not a part of the radicand. Our radicand here is 7. The square root of 7 is going to be an irrational number because 7 is not a perfect square, right? 9 is a perfect square. The square root of 9 is 3. 4 is a perfect square. The square root of 4 is 2. Because 7 is somewhere between 9 and 4, the square root of 7 is going to be somewhere between 2 and 3, but it's going to be an irrational number, some number that we cannot write as a fraction, some number in the calculator that's going to be a continuation of decimal values that is non-repeating. It's irrational, just like the number pi. It is irrational, just like E, the natural letter E. It is irrational. However, if you square the square root of 7, the exponent of 2 and the radical sign will cancel, leaving us with a result of 7. Yes, our index and our exponent are even, but our index is not underneath the radical sign, so we do not have to worry about any absolute value outcomes. For part C, it follows property 1 that we are squaring the square root of 7, thus the exponent and the radical cancel. For part C, we get 7. And this is our simplification. This is our evaluation using inverse properties. For part D, however, what is our radicand? Our radicand is the square of negative 3. In other words, negative 3 raised to the power of 2. We are taking the square root of our radicand, negative 3 to the power of 2. Notice this fits property 2, where n is even, n equals 2, the square root. Thus, if we were to cancel the exponent of 2 and our square root sign, we're left with negative 3. But we're reminded to take the absolute value of negative 3. In other words, for part D, when we cancel the exponent with the radical, extracting that out of the radical there, we can't pull a negative 3 out because we can't have a negative under the radical sign. Thus, we change negative 3 to positive 3. For part D, evaluating the expression, part D, that represents the number 3. And why is this the case? If you square negative 3, what happens? Squaring negative 3 squared is positive 9. So our radicand there is actually positive 9. The square root of positive 9 is positive 3. Thus, part D, it follows property 2 when n is even. The nth root of a to the n is equal to the absolute value of a. In other words, when you cancel the exponent and the radical, the absolute value of negative 3 is positive 3 because the square of negative 3 is 9 and taking the square root of 9 is positive 3. For part E, we are taking the square root of what? Our radicand is the negative of 3 squared. Notice the similarities for parts D and E. Notice the differences. For part D, there's parentheses involved. What does the parentheses indicate in mathematics? A grouping. For part D, we are grouping a negative and a 3. So what's being squared for part D? For part D, the negative 3 is being squared, resulting in a positive 9. For part E, there is no parentheses, therefore there is no grouping. What's being squared in part E? Under our square root sign, we have a negative and we have a 3 that's being squared. For part E, negative 3 is not being squared. That's happening in part D. The parentheses indicates in part D that the negative 3 is being squared. For part E, no parentheses, therefore the number 3 is being squared. Part E says we have the square root of the negative of 3 squared. So we simplify 3 squared is 9. So for part E, a negative 3 squared where 3 squared is 9, we have a negative 9 under the radical. And thus the square root of negative 9, what is the number such that when you square it, it gives you negative 9? Well, 3 squared is positive 9. Squaring negative 3 is positive 9. Thus for part E, when you take the square root of a negative number, this is considered to be a non-real number. In section 6, we will define this to be an imaginary number. For exercises 55 through 60, we will evaluate the radical expression without using a calculator. If not possible, state the reason. For number 55, cubic root of 10 to the third power. 56, cubic root of 4 to the third power. 57, we have the negative of the cubic root of negative 6 to the third power. 58, we have the negative of the cubic root of 9 to the third power. For 59, we have the cubic root of negative 1/4 raised to the third power. And for number 60, we have the negative of the cubic root of 1/5 raised to the third power. We'll go to the full view here. And for number 55, immediately as you see here, our exponent 3, our index is the same. They are odd numbers. Thus, by canceling the radical with the exponent, we get 10. For number 55, we evaluate to get 10. Why? Under the radical, 10 to the power of 3, 10 multiplied 10 multiplied 10. 10 times 10 is 100, times 10 is 1,000. Thus, if 10 cubed equals 1,000, this defines the cubic root of 10,000, or excuse me, the cubic root of 1,000 to be 10. Thus, we have, simplifying our radicand 1,000, the cubic root of 1,000. Well, this surely equals 10 because 10 cubed is 1,000, thus the cubic root of 1,000 is 10. We can view that initially by canceling the exponent with its like index of 3, leaving us with 10. We use this for number 56, canceling, we get 4. And this is because 4 to the third power, 4 times 4 times 4 is 64. The cubic root of 64 then is equal to 4. For number 57, exponent of 3, thus odd exponent, that same as our index here, we cancel. We're left with negative 6, but we want the negative of negative 6. In other words, if we have a negative multiply a negative 6, the negatives cancel, leaving us with the positive 6. And we can see this because what happens when you cube negative 6? 3 factors of negative 6. Negative 6 multiply negative 6 is positive 36. Multiply another negative 6 is negative 216. Thus, the cubic root of negative 216 is negative 6. But if we have the negative of negative 6, this is saying what is the opposite of negative 6? Well, that's positive 6. So for number 57, negatives cancel, giving us positive 6. What about 58? Once again, we have the negative of some number. What is the negative of this number? The cubic root of 9 cubed, exponent is odd. Thus, we can make the cancellation because they are like. We have 9, but we want the negative of 9 or the opposite of 9. What is the opposite of 9? Well, that's negative 9. Throwing the negative in front of the positive, we get a negative 9. Again, this is because 9 to the third power, 729, I believe. Let's take a look at that. Let's go to Desmos. 9 to the third power, and let's show again why is, 729, sorry. 9 to the third power is 729. Why? It's because 9, how is it defined? Exponents mean repeated multiplication. 9 to the third power is 9 times 9 times 9, which of course is 729. These represent the same exact values. They express the same thing. Thus here, for our, going back to our full view, Because 9 to the third power is 729, if we take the cubic root right here, our nth root, there's our new radical notation we can work with here, our nth root radical notation. It allows us to change our index to 3, and thus what is the cubic root of 729? Of course it equals 9, because 9 cubed equals 729. This shows that 3 factors of 9, if our base is 9 and our power is 3, to get 729, then the cube root of 729, in other words, what number such that when you have a power of 3 gives you 729, it's 9. So there's that relationship. That's why there's a cancellation. That's why it is equal to 9 underneath the radical. But now attaching the negative out front, we get the negative 9. Lastly here, as we see once more, cubic root of the fraction. Oh, we're introducing fractions now. But notice here that this fraction is very specific. What do we see? The number 1 is a perfect square. 1 is a perfect cube. 1 is a perfect fourth power, right? 1 raised to any integer power is always going to equal 1. 1 to the negative 5 power is 1 divided by 1 to the fifth, which is 1. No matter what, 1 raised to any power is always going to equal 1. So it's a perfect anything. In this case, it is a perfect cube. What about 4 though? That's not interesting. But that's the case though, right? Is that we're not taking the cubic root of 4. We're actually taking the cubic root of the negative 1/4 to the power of 3. That's what's going to make things interesting, because what does this mean here? If we have negative 1/4 to the power of 3, we have 3 factors of negative 1/4. This is the same as having 3 negative factors, which is going to result in a negative value, right? If you have 3 negative factors, it will be negative. Now what happens here? When you cube a fraction, when you raise a fraction to a power, really what's happening here is you're raising the numerator to the power. So 1 to the power of 3 is 1. 4 to the power of 3, 4 cubed, 4 times 4 times 4 is 64. And thus the cubic root of negative 1/64 is going to give us negative 1/4. And why is that? Using our inverse property, because our exponent here and our base, our index is the same, and they're odd numbers, they cancel, leaving us with the base value of negative 1/4. That's because if we work this out mathematically, multiply negative 1/4 to itself 3 times, negative 1/4 multiply negative 1/4 multiply negative 1/4, this results in a negative 1/64. And because 3 factors of negative 1/4 gives us negative 1/64, this defines the cube root of negative 1/64 to be negative 1/4. And we see that simply by making our cancellations. However, if our exponent and our index happen to be even numbers, such as if this was a 4 and this was a 4, or if this was a 2 and 2, then by making the cancellation, we then would have to put our absolute values around it and make it positive. And that is because negative 1/4 to any positive even power, such as 2, 4, 6, 8, etc., will result in a positive output. Thus, our radicand underneath, although it would be some negative number to some even power, a negative number to a power that is even, that is positive. Thus, if our radicand is positive, our output must also be positive. They must match up. However, here, cubing negative 1/4 is negative 1/64. Thus, when we take the cube root of negative 1/64, our output must have the same sign as our radicand. Our radicand here is negative 1/64. It's expressed as a number to a power, but notice again here, this is our radicand when written out. That radicand is negative, thus our output must be negative. We note because we have an odd exponent, a negative number to an odd exponent is always going to be negative. Thus, making our cancellations, we get the negative 1/4. Lastly here, for number 60, what do we think there? We have the negative of the cubic root of 1/5 to the third power. For number 60 here, the cubic root and the exponent of 3, because the index and exponent are the same value and they are odd, we make the cancellation and we have 1/5. But for number 60, we want the negative of 1/5. In other words, we want the opposite of 1/5. 1/5 is positive. Thus, for number 60, this simplifies down into the fraction negative 1/5.